You're one of the co-founders of Puralink.
I got into robotics quite early. Robotics was still relatively early.
Is there like an LLM moment for robotics?
Enable thousands of robots to simultaneously run and learn. Data is the key. Make robots that just live in water pipes, finding leaks before they ever become a massive problem. Getting an exact location of where a defect is, or even where a pipe as a whole is super valuable. Create that force that's required to overcome gravity and actually go upwards. We want to facilitate is an ecosystem of companies building on top of our robot. Globally, 30% of all our fresh drinking water is lost to pipe leaks.
Just go and do it and see what happens.
Ideas are worth like jack shit, absolute jack shit. Like if you can't execute, there's nothing.
Just take that initiative to actually take whatever crazy ideas that they might have and just try to see what comes of it.
Don't be afraid of ambition. Chase it, love it, wrap your arms around it and say it out loud.
New Zealanders don't know any better. They will just get up and give it a shot. That's why we were first to get to the top of Mount Everest.
Go to dream that ultimate dream. Like, what is it that you ultimately want to do? And it's all achievable.
Great, Harrison. Thank you so much for joining us on TechMates.
Thanks for having me.
Yeah, awesome. So you're one of the co-founders of PureLink, one of our 2025 investments. Super excited to be on board. You're based in Sydney. I've actually visited your office a few months ago. It's a super cool kind of house close to the CBD. You should actually come sometime. It's really cool to check out. But yeah, we want to obviously understand everything about Puralink and your background. I've seen on your LinkedIn that you've been in robotics ever since you went to university, right? So I want to understand a little bit your fascination with it. Yeah, maybe tell us a little bit more about like what your kind of childhood was like and when you first came across robotics.
Yeah, for sure. I got into robotics quite early. So I was lucky in that thread. My high school had a robotics club, and I think I was maybe 12 or 13 years old, and it was centered around the EV3 Lego Mindstorms platform. So it was kind of an easy way for me to get my head around robotics. You know, I was basically playing with Lego and drag and drop programming, and then just fell in love with it. So that spiraled into working with Arduinos and doing more complex robotics projects. I'd consider myself a pretty competitive person. So there were robotics competitions that I joined. So I was doing that for school and also the University of New South Wales while I was at high school. Yeah, it really just immersed me in the world of robotics. So I then went to study software engineering at the University of Technology, Sydney. So stepped a little bit further away from the hardware and physical side of engineering, more into the software and data science side. And that's how I ended up meeting Shion, my co-founder at PureLink. I did an internship at AWS.
Harrison, was there anything that like inspired you or made you kind of think like this was really, really cool, like from the point of view of robotics?
I think it was the fact that you could make decisions and make, solve problems and see them actuated in the real world. So I enjoy programming. It's a lot of fun, but there's a difference between, writing something and seeing it pop up on a screen and seeing something physically move in front of you and make decisions without you having any input. So I think that's what really inspired me. The amount of problems I could solve, the amount of applications I could see were kind of endless.
What was the first time you kind of like experienced that?
I think it was robotic soccer. So I would have been in my early years of high school, and I was making a robot that would follow this infrared ball around a field and try and score it in a little goal. And I remember spending so long bug fixing and prototyping and getting this up and running, and then to see it actually playing against other little robots and, making decisions and achieving a goal completely independently of someone controlling it was just such an unlock. I found it really exciting.
Were your friends excited about robotics as well, or was that kind of like your own passion?
There were definitely friends who had their own things. I had friends through robotics as well, so that was a good way to bond with them. But it was definitely not something everyone was doing. Robotics was still relatively early, like it was coming into its own. So I was lucky I got involved when I did.
And then you made the decision, to study at UTS in Sydney. Did you always know you wanted to go down that sort of route, engineering, software, hardware, or did you consider something else?
Yeah, I was tossing up between mechatronics, which is basically just the study of everything involved with robotics, or specializing in one specific aspect of it. So whether it's like mechanical, electrical, or software, I really enjoyed the kind of algorithmic side of things of software engineering. And so that's the path I ended up pursuing. But I very quickly found that I was missing a lot of the other like physical parts of working on a robot.
What was your kind of favorite part in all? Yeah, because I think mechatronics, you get to kind of work on every aspect, right? Mechanics, electronics, the integrated systems, the controls. Like, what was your kind of, did you have any kind of like part that you really enjoyed?
Did really enjoy the software side, which is what led me towards that. But I think part of the fun of robotics is that you really can't just put yourself in a niche. There's so many different things that go into a robot moving that you need to be cross-functional. You need to be able to identify if something's going wrong with your electrical systems, with your motors, your hardware. There's so much that goes into it that isolating yourself in just like a little software box doesn't really work.
Interesting.
While you were in high school, you competed in a bunch of challenges as well, right? Were the kind of other kids, were they all your age, or were you more on the younger side, I guess?
Yeah, definitely when I started, I was on the younger side. That's a good thing, I think, about a lot of the student teams and robotics competitions that exist at the moment is there's this kind of level of mentorship that goes on. So you'll get paired with students who might be 2-3 years ahead of you, and you'll just be able to absorb information from them and learn as you work on the same projects. So on my school team, I eventually moved into that role, helping to upskill younger students. And the same went on the university team while I was in high school. That was really great to be able to work with mentors who were, either qualified engineers or studying engineering before I had even graduated high school.
What was the coolest thing that you built? Ever, besides PureLink?
Besides PureLink, I think as part of the first robotics challenge, so FRC competitions, we'd work on these robots that were massive comparatively to my high school stuff, or even to the PureLink robot, which is quite a small unit. These were, 70 to 80 kilos, quite large. And I remember one year, one of the challenges was it had to grapple and grab a bar and essentially pull itself up. And there was a lot that went into the engineering system behind that. And I think seeing that actually lift itself into the air for the first time was a really cool moment.
How did y'all? Because so first robotics. I mean, like for context, this is like a big competition. I think is it global? I thought it was mostly in the U.S., but I guess it's global. And basically, they're just like arbitrary just challenges that like what you said. I saw one where it was just like there are these like kind of like spindles you had to like put onto like a tree, basically. I think that was a challenge one of the years. And there's all kinds of different interesting creative solutions that kids come up with to solve these. And basically you have like, you're pretty much unlimited in like what you can do, right? Like there's no constraints, but usually you have like a team and then like a coach. And usually there's a bunch of like, kind of like you're working within a team's kind of like design guidelines and structure. Right?
Yeah, exactly. I mean, you have like simple things like size constraints and power constraints to make sure, nothing's too dangerous. But it gives you the freedom to problem solve, and the different approaches that you see from all the different teams all over the world approaching the same problem essentially is really inspiring. I remember you'd have robot reveal just before the competition start, and you'd be able to watch like there were teams that would work with NASA engineers and all sorts of crazy systems would come out. And it was a lot of fun.
Were there any like heuristics that you learned from that whole thing? Because like, I think there's always like that's a cool thing about engineering is you can solve the problem in a lot of different ways, but it matters which constraints you're like prioritizing. So what were the like heuristics and like, I don't know, I guess mental models that you picked up from that experience?
I think my favorite one is the best part is no part. It follows the same vein as KISS, or keep it simple, stupid. It's one of those rules of thumb that it sounds really simple to say, but when you actually try and take a complex problem or system and boil it down to what's really just essential, what's the most simple way to solve this problem, it's actually quite a hard thing to do from an engineering perspective. And I think it has compounding benefits when you look at the long-term performance or operation from a maintenance perspective of pretty much any system. So that's one I learned early the hard way, and I've continued to kind of implement.
How'd you learn that the hard way? What was the story there?
I think the first soccer robot that I built had way too many actuators and sensors on it. I had, it was omnidirectionally driven, it had 4 motors. So there was a whole bunch of maths that went into like keeping it strafing around the field. And there was a little kicker, so it would like actuate there. And then you had like a vision system and a compass, gyro sensor. There was so much going on that all it took was one thing to be slightly off and the system wouldn't work. And so although it would have been amazing to get everything up and running all at the same time, it was often by boiling it down to just what was essential that you'd get the best performance and the most consistency out of a solution.
And I guess like building stuff at that time, I mean, maybe even now for students, like it kind of feels like it was trying to build like AI systems before LLMs. Like, so if you look at software, like the equivalent sort of thing, right? Because you have to like sort of literally like engineer every single part of the system and like set constraints and then like literally test it in the real world, I guess, to like figure out where it goes wrong, what are the edge cases. Because I guess because you have to sort of predict everything yourself, right? Whereas like, is it now, I guess, yeah. So like, is there like an LLM moment for robotics? Like, has that already come, or like, do you think that will come at some point? And yeah, will we see like an explosion of kind of robotics products and systems coming out after that happens?
I think we're on the cusp of it at the moment, because one of the big things that robots have struggled traditionally to handle is edge cases. So a robot, even now today, that has been trained on any particular environment, or even if it's using deterministic methods like kinematics and pre-programmed path planning, if you throw something that it's never seen before or that it didn't account for, it causes problems. And that can cause safety issues when you put it around people, or it can just really lose the effectiveness of that robot in whatever application it's in. And I think now with the ability to fuse synthetic data and a whole bunch of reinforcement learning and like hierarchical agents in terms of like split decision making between aspects of the system, you're seeing an explosion in what robots are able to do. And subsequently, that's just going to lead to more and more applications where robots become feasible.
And like with LLMs, I guess it was like this transformer architecture plus like a bunch of data, right? And just happened to like scale the data and just need more data basically and better chips. Like, do you think what's the equivalent in robotics, or do you think it's because in robotics like there's a bunch of things there. There's like the mechanical side, and there's like some kind of intelligence to control that. There's also, I mean, there's like the vision piece, right? Like, what's the right kind of mental model to think about that? Is like different kind of like silos, or is there just one? Do you think it'll eventually be like one model that just like does everything?
Yeah, it has been very siloed up until now, but I think with approaches like the NVIDIA Omniverse system, where the idea is you model everything to do with the robot down to the gears and the amount of friction that you'll experience in gearboxes into a simulated environment, and then enable thousands of robots to simultaneously run and learn. It creates scale and a sense of efficiency that we've never been able to get before. And that unified approach is already achieving really incredible results. I mean, we see it with some of the unitary robots that we see doing crazy things. And I know companies like Boston Dynamics and Anybotics are also taking that approach and getting really incredible outcomes that could never have been achieved through these more siloed traditional methods.
Yeah, interesting. I mean, Boston Dynamics is pretty cool, right? It feels like it's sort of, and I guess, yeah, you've seen a lot of these like Chinese like kind of companies now come out and demonstrate some really interesting stuff where it feels like those robots, whether it's like biped or a quadruped, like they actually have some intelligence in the way that like they can actually balance and get up and actually like get to a goal, even if there's obstacles and people are like antagonistic towards them and stuff, right?
Yeah, it's pretty interesting to see how fast it's evolved, because I feel like this sense of the AI revolution on the software side is making people focus on how that can be applied to robotics and the physical embodiments of AI even more. So I think the pace of innovation on that front is only going to continue, and we're seeing quadrupeds and bipeds sprouting up everywhere for all sorts of different applications. So the amount of data that everyone's collecting is only going to compound that.
Do LLMs kind of enable faster development?
From a developer side, absolutely. I guess even from a general engineering side, it's easier to go through the problem solving and kind of engineering design process when you've got almost like an engineering co-pilot with limitless amounts of information at hand. That's definitely creating a lot of efficiencies in terms of the per engineer output. But I think the implementation of those same types of models, maybe not LLM, but like VLM models on robots, is creating so much more intelligent applications for robots that we haven't seen before.
Interesting. And so what is the what is the mental model that you have for like how robotics improves? Like, and again, like right now, I think a lot of people have this idea of LLMs now in their minds is like, oh, here's like this thing, and like if you get more data, it sort of gets more intelligent, and there's proprietary models that are sort of better. There's like open source models that anyone can use and run, and you can sort of like give them individual kind of context of your documents or whatever, and then they sort of are intelligent on your stuff. Like, again, what's like the mental model that you have for thinking about robotics? Is there like an analogous one to LLMs, or is it like completely different?
I think it's pretty analogous to LLMs in the sense that data is the key. But instead of having, 30, the entire human history worth of written knowledge to train on and to consume, there's not as much that exists for robots. So yes, you've got video footage, but how that translates into actuation of a physical embodiment of AI is not something that there's existing data out there on. So that's why I think these applications that we're getting from especially humanoid companies where they've got human controllers, essentially just data labeling, but at scale. So you'll start to see when these humanoid systems roll out, there will be people working remotely, controlling these robots, doing these simple tasks like putting washing away or whatever the case may be for a household robot. And people will say this isn't true AI, it's just remote control, but it's kind of a step on the ladder to get to the amount of data that you need to really make these truly autonomous. So I think it'll be similar, but it'll take a little bit longer just because of the data availability.
And I guess with the data, right? Like with LLMs, like the data, there's a lot of data on the internet and a lot of it's freely available. And whereas with robotics, it's like, it's unclear where you get the data, right? Do you have to like first build the hardware first and then gather the data? And if so, like, is there any kind of like, like that feels like that would really limit the number of players that would be able to actually build enough hardware to get enough data to then improve, right? Like it feels like it just limits it to like the really big players compared to like LLMs where like, a random kind of company in China can build like an LLM that's better than, than OpenAI for a certain amount of time.
Yeah, there'll definitely be training approaches and ways of creating more effective robots with less. I think synthetic data is a big opportunity for that. But I also think there's a lot of consolidation at the moment in form factor. So the more robots that exist in the same form factor will lead to easier training for those form factors. So it's quadrupeds and bipeds are really obvious ones that we can see. There are so many companies popping up, essentially creating similar form factors and can all benefit from the evolution of that industry from a training perspective. Unfortunately, PureLink has a very unique form factor for our robots, so we can't exactly jump on the same benefits trend, but it's definitely something that I think will continue to spiral.
Interesting. So you think form factors will converge because of the training data and the availability of training data?
Yeah, I mean, there will definitely always be reasons to create different form factors for specific applications, but the more intelligent a robot needs to be, the more widespread its use cases, the easier it is to converge on form factor and just collect significant amounts of data.
Maybe before we go into Puralink, kind of curious on you kind of started talking a little bit about this. You mentioned you met your co-founder in the University of Technology for UTS in Sydney.
Yeah.
Tell us a bit more about like how you met and when you started working, or just when you started working together.
Yeah, so we didn't meet at UTS actually. We both just happened to go to the same university, but we met as interns at Amazon Web Services. We were at AWS. Shion had worked at IBM for a couple of years and had come across. And he was in a more commercial sense. He was in business development. I was in cloud solutions architecture. And one of the jobs he had at the start of that year was essentially to populate this massive list of greenfield potential customers, go on their website, research into them. And he was filling it out in Excel. And I think there were 2,500 different potential companies that he had to kind of go through one by one. And I remember sitting there and going, I can automate that. I reckon I can write a script that'll scrape their website and kind of boil it down into all the key information you need, and we can get this done in a couple hours instead of you spending the next, 4 weeks on this. And I guess I was very used to building solutions and solving problems and then setting and forgetting almost. And what ended up happening was I built this really effective tool, and Shion took that and kind of communicated and sold it to the wider org to the point where AWS built like a team around it, and it was known by a lot of people inside the organization. There was a whole bunch of impact that was driven from it. And I had been working on the ferret, or just this pipe robotics project as it was at the time, through my engineering capstone thesis. And I was chatting to him about it towards the end of our internship. He was taken aback by the scale, the magnitude of pipes that exist around us from under our feet with, what's that, Zach?
Get into it. Like, how did you find this problem and get interested in solving it?
That's a great question. Here in Sydney in 2019, we had the bushfires, we had the droughts, we were under stage 2 water restrictions, so you can't wash your car, you can't water your garden, all of that good stuff. And I was leaving for work at the time, and I was presented with this massive pipe leak, essentially, that turned my street into a river. The amount of water that was being lost was enough that everyone on the street, let alone the surrounding, suburb, could have been out of water restrictions very easily. And so when, the repair team finally showed up, they started digging. They couldn't find exactly where the leak was, so they kept digging and digging. And just at the end of the whole process, it was very clear to me how inefficient, and it looked really expensive, as well as being disruptive to everyone on the street. And I thought very naively at the time, of course, surely there's a way that robots could do this. Surely there's a way we could put a robot in the pipe and it could go and find the leak and maybe even patch it from the inside. And that's kind of what got me started on this path that's led to PureLink today.
So you got delayed going to work.
Exactly.
By a flood. And you were like so eager to go to work. You're like, I gotta solve this problem.
Definitely. It was really just how in my face it was. Maybe it was just a way that I had kind of learnt to think doing so much robotics in terms of the problem solving. And I don't know, I saw a big problem and I figured maybe I can give it a go in terms of solving it.
So you spent, I guess, the first few years trying to figure out the technical solution to this problem, right? Like, can I build a robot that's doing the inspection of it? And then did you partner up with Shion to kind of figure out, okay, is there also a commercial case, or did you already discover that before you bought them?
Yeah, so the initial idea behind PureLink was what's now our moonshot. It's to put robots in live water pipes. And if you think about the amount of kinetic energy that's flowing through a pipe, you should be able to recharge off that water that's flowing past you. And essentially you can make robots that just live in water pipes, finding leaks before they ever become a massive problem. So that has, that's a big, big goal, a massive dream. And it's something we're working towards achieving at PureLink, but it also wasn't the best starting point for commercialization. So I think Shion was able to bring that sense of practicality. He had that commercial mind and focus, and was able to help me synthesize more of a staged plan to get there, and a way to commercialize all the different problem solving and challenges that we were essentially engineering solutions to along the way to achieve this grand vision.
So what was the first kind of commercial problem that you thought you can kind of solve? I guess, yeah, the long-term goal is clear, but how did you think, okay, like, how can we make this useful for somebody?
Yeah. So the first problem that we solved was, how do you navigate inside a pipe? So down at these smallish diameters, so street level, 150 mil or 6 inch, how do you make a robot that can get through corners, intersections, even go up vertical for cities, all in one form factor? And so we achieved that. We now have a patent on that technology, and the low-hanging fruit from that was inspection. So especially in the sewage and wastewater industry, where the regulatory barrier is lowered to get in, you're not putting this in people's fresh drinking water, you're not putting it in gas pipes, which are explosive. That was the first market that we identified. It's massive. These pipes are everywhere. Everyone's got sewage connected to their homes here in Australia. And it was a way that we could start putting our robots out in the field and commercializing what we were building.
Interesting. Can you tell us about how pipes work? So like it's funny, actually my first company was named Piper because it was just like analogy to like the pipes under our homes, and that like, without them we'd have like we couldn't have the like 21st century kind of like modern living that we like kind of take for granted. But we don't really understand how they all work. And like the analogy was the same thing for like applies to like computers. And so like our product was like this thing that taught kids like how to build computers. So that's why it's called Piper. That was the analogy. So that's like how we explained it. But like I still don't know how pipes work. I understand how computers work, but not pipes. So yeah, I mean, like, so I assume there's like some piping that goes from like your toilet and shower and sink out, and there's pipes that bring some water in. And is it just like as simple as that? There's just like a big place somewhere that just like pumps the water in, and then kind of like somewhere that like takes the wastewater, or is there some more complexity there? And yeah, kind of what did you learn, I guess, about this whole like space of piping?
There's a lot of complexity and also a lot of, I would say, compromise, because these systems have been around, in some places, especially in places like the UK, for hundreds of years. So you're working with infrastructure that was installed yesterday that connects to infrastructure that's been around for, 150 years. And you've got to make everything work together at the same time. It's quite a complex kind of patchwork of different eras. So on the sewage and wastewater side, there's been a lot of improvements. I mean, sanitation is a massive part of allowing so many people that live in our cities to live in such close proximity to each other. And so there's been a lot of transition away from sewage that's connected to stormwater and wastewater, so it doesn't kind of just overflow into rivers and into the environment around us. So we've got massive wastewater processing stations, and they're limited in the amount of water that they can actually, or wastewater that they can process at any given point in time. So there's been, especially in Australia, we have a separated stormwater and sewage system, which allows us to route sewage to these wastewater processing plants, and then stormwater can go more easily into runoffs into the ocean. But what this means is if you get any infiltration into your sewage system, so any cracks in the pipes that is allowing groundwater from the water table into these pipes, it can overwhelm these processing. So it's actually really important that, although on the live water space, you're really trying to make sure that the water doesn't get out, it doesn't leak. On the sewage space, you're trying to do almost the opposite and make sure that water and tree roots and other things can't get in. So yeah, there's a lot of different ages of pipes. So you've got pipes that are concrete or stone, or you've got more modern PVC pipes and terracotta. There's so many different materials that go into it as well, that it creates this, like I said, a patchwork system.
And who is responsible for making sure this patchwork system works?
Yeah, so you've got multiple levels there. You've got the asset owners, so people like Sydney Water or Melbourne Water, who are really responsible for the overall system. So making sure that people are connected, making sure that the pipes are kept intact, but they're not necessarily the ones doing the work. So they will tender and subcontract out a lot of this maintenance and remedial work and proactive maintenance to all sorts of contractors. So there's an entire ecosystem of service providers and contractors who will bid for a lot of this work. So I think in Sydney, there's, more than 50 independent service providers that all have their own service teams that will go on sites and do these works. At PureLink, we work with these service providers in this ecosystem layer that sits below the asset owner.
And how do they currently service these pipes? How do they inspect it? How do they fix them?
Yeah, so there's a lot of digging, to put it lightly. There is camera inspection of these pipes. There's a few tools that they currently use for inspection. So you've got push rod cameras, which you might have seen before. It kind of looks like a camera on a hose, and they'll just push it down into a pipe. Can't get very far. It's very limited in terms of its navigation capabilities, and you're also sometimes getting these stuck. So they'll have to cut off the tool, leave it in the pipe. There's all sorts of problems that go into that. The other side of things, especially when you get into your larger pipes, are essentially like glorified RC cars, so remote control cars. They'll exist like 4 wheels on the bottom of the pipe, and they'll drive through with a camera on them. So These tools were innovative maybe 20, 25 years ago, but they struggle with inclines. They can't do corners. They definitely can't do vertical pipes. And so they're very limited in the places at which they can go.
And what's your pitch to them? Where you go out and pitch this robot? I mean, obviously it's cool. It looks great. But like, what's the kind of broader pitch to them?
I mean, maybe, I don't know, like maybe before we get into like the pitch, could you take us through like, how you started learning about this space and developing a thesis for like, what is the right wedge into the market? Like, what is the problem that like they're trying to solve? What's the problem that like is like the biggest problem? Because like, I guess like one can imagine that, in theory it'd be cool to have these robots, but one can also imagine that like maybe this is all administered by the government or who's like inefficient, doesn't care, and like they have no incentive to like innovate or get this to be cheaper or faster or whatever. Like I think when you start interfacing with government, like especially the larger kind of scale of government, like it's like the incentives are really misaligned. Like they principal agent problem really kind of like rears its head, and like it's in theory something like makes a lot of sense. It just doesn't get done because no one's incentivized to get it done. So yeah, like how did you like kind of think about what's the problem and what's the right way to sort of enter the market? Like,
I mean, it was
maybe
definitely a lot of trial and error coming from the robotics space and not from the utility or infrastructure space. There was a lot of learning that we had to do. I think the first point of call, and I think most people will think of the utility as the first point of contact for pipe infrastructure. So that was our initial thought, and that's where we tried to start our journey. Obviously, we very quickly found out that they don't have large service teams, and they're not the ones that are traditionally maintaining these assets themselves. They're also operating at such a scale that it's really hard to sell into as a startup. So even the utilities that might be open to technology and might have their own service teams are looking more at your larger providers rather than working with, on the other side of that, we then went to like your big civil contractor and infrastructure companies. So we're approaching, the companies that are making the buildings and everything that we see in our cities. And we very quickly found that they also were contracting out this work to service providers. And initially we thought that service providers would have an incentive to not find efficiencies and not reduce the cost, because that would reduce the total cut that they can take on these jobs. All it took was talking to them to find out that that's not the case. It's a hyper competitive industry. There are so many service providers that they're all tendering against. They're all looking for an edge on each other. It's also a very low margin business. So they're looking for ways in which they can increase their efficiency to essentially make more money at the end of the day. So a lot of these companies that we approach, we are showing them the benefits and the optimizations and the competitive edge that a PureLink robot gives them over existing tools on the market.
But like, what exactly was the problem that you identified that they had or that you thought you could solve?
It was access. So initially it was really like, you don't have to dig as often because you can access these pipes in other means. And we quickly identified that they didn't know where a lot of the pipes were geographically, so that the mapping systems were outdated. And so getting an exact location of where a defect is, or even where a pipe as a whole is super valuable. So that was the initial problem that we found was crucial for us to solve getting into the industry.
But like, I guess, what is the job they have that needs to be done? Is it like someone's like, hey, we have a leak, or we think we have a leak, or like what exactly is like the task they need to perform?
So there are different kind of tendering jobs that they can be given. So there's reactive maintenance. So they'll get called out to a site and they will have to find out what's wrong. They'll need to go in and inspect the pipe and dig and try and fix whatever's happened. There's proactive work where they're going in and checking pipes. So they're going through and checking that critical pieces of infrastructure haven't collapsed. There's no existing problems. And so they'll be given, a map of all sorts of different areas to go out and send service teams on a daily basis to go and inspect. And then you've also got new commissioning of infrastructure. So in Sydney, we've got the new airport region around Badgerys Creek, and there's a lot of development going on out there. And Sydney Water's spending billions installing all the infrastructure that's required to support those systems. So what that means is every time they install a pipe, they've got to go in and check that it's been installed correctly. They've got to check that it connects to the existing network properly. And so these are all times when they have to inspect camera or otherwise these pipes to validate.
So getting access to the pipes was the hardest thing, basically. And you're saying they have some so and part of it is like they don't know where the pipes are. And then if they know where the pipes are, they don't know how to get inside to inspect it. Is that kind of the...
Yeah, essentially. The tools that they have at the moment are limited in terms of how far they can go, what they can encounter. So then they're often having to move around to try and inspect the same pipe from different angles and different entry points. And it just creates a lot of inefficiencies and a lot of wasted time on their end, which at the end of the day cuts into their profits.
Interesting. I see. And but I guess another product you could have built was I don't know, some kind of scanning system that would tell them exactly where the pipes are, right? Something that just sits there and maybe, I don't know, sends some kind of signal down, detects the pipes, tells them, hey, the pipes are actually right here, dig here. And that seems like a maybe slightly easier problem to solve than a pipe inspection robot. Why didn't you go after that?
There are a lot of nuances that go into it. And there are definitely companies that do ground penetrating radar and things like that. The problem is, these pipes are all sorts of different materials. So that creates challenges in terms of detecting them. And they're also in, often hard to reach areas. So they might be, there's ones that go under the Sydney Harbour. There's ones that are under super busy motorways, in buildings that go down the spine of them in the central column. They're in places where it's almost impossible to access with those kinds of tools. And the thesis behind PureLink as well is inspection is the low-hanging fruit. But really, once you start building on top of this platform, which provides access, you can do more advanced things like patchwork repair or spot welding or, more advanced repair and active maintenance than just finding exactly where the leak is.
So when you identified that the problem was access, what were your hypotheses for how to solve that problem?
Yeah, I think the biggest part of it is the size constraints and form factor problem that you have to solve. So the industry as a whole at the moment, that has been the limiting factor. When you turn the corner of a pipe, you essentially have a spheroid shape of volume that would fit around that corner. And so whatever robot format that you end up choosing needs to either be compliant, so it needs to bend around that corner, or it needs to fit within that entire space itself. And so what we started with was a way to actuate and control wheels in a really small form factor amount of space. So we have a patent on a system that allows us to omnidirectionally drive and rotate wheels, large wheels, in these small form factor spaces by working around the wheel itself, which means that you don't take up that vertical form factor. I actually have the ferret here. It's a good visual aid. It won't help for the people listening. Essentially, it's articulating, as I mentioned, so it can bend around these corners and intersection. But the first piece of technology that sits on this that we developed is what drives these wheels. So you need quite large wheels to get around, all the debris and stuff that you find inside pipes. But also we need to be able to independently articulate and drive these wheels with quite a high amount of force or torque. So these wheels now can compress against the walls of the pipe, but they can also be independently turned and driven in this really small cylindrical shape, which is, a limitation that has plagued a lot of the existing tools in terms of what size pipes they can fit in.
Interesting. Why didn't you guys, because you also could have, you've seen the Sphero robot?
No.
It's like a kid's toy. I don't know if the company exists anymore. There's a kid's coding robot called Sphero. It's just just what you'd imagine is like a sphere. And then, just roll around. You just control it on your phone and stuff. Yeah, why didn't you guys go for something like that?
Yeah, I'm trying to picture the form factor. The biggest thing about this embodiment of a robot is you also get the traction to go vertical. So these pipes exist in a lot of different orientations, especially outside of just the water industry. When you look at oil and gas and data centers and food processing and irrigation, there's a lot of vertical pipes, and those are even harder for existing systems to access. The thesis that we had in developing this was, we've seen how much impact drones have had above ground. We want to create the universal platform that creates that access, but for below ground infrastructure and pipes. And so this embodiment needed to be able to navigate all different configurations, corners, vertical orientations, anything you wanted to do inside a pipe, we wanted to be able to facilitate with the PureLink robot.
Can you explain how it goes up vertically? Like how,
So if you imagine, I can show you how it would physically do it. If it's driving along a pipe like this, we can change the orientation of the wheels, which are compressing against the side of the pipe, which allows it to then change its orientation. Then if we face back straight, we can then start turning and bending around that corner to go up. These wheels are, as I mentioned earlier, compressing against the side of the pipe. So what that allows them to do is create that traction, create that force that's required to overcome gravity and actually go upwards.
Aren't you with that form factor, aren't you sort of constrained by maximum pipe size? Like if the pipe is like any bigger than the maximum kind of extension of the wheels, you have no traction?
Yes. On this variation, yes. So we do have some workarounds to allow it to operate in any pipe size in a horizontal kind of orientation. But when you're going vertically, you need to be able to essentially compress against the walls of the pipe as a compression crawler. And then that's what allows you to go upwards. So the good part about that is most networks are pretty standardized in terms of their size of pipes. You have a whole bunch of fluid dynamics that goes into it. And so you'll get 6-inch pipe networks. You'll get 150 mil, 225s. There's like standards that you keep to, which is good.
Are there pipes that are bigger?
Yeah.
Like, and what the current ferret can do?
Yeah. They're a huge pipe. I mean, pipes get up to like multiple meters in internal diameter. The interesting part about those is the bigger the pipe is, the more critical it is, which means the more investment has already gone into maintaining those pipe networks. So they will have periods at which people will go through they'll have large robotic systems that have been developed that are, millions of dollars per unit to inspect these pipes and make sure that, they haven't failed. And so this was a segment of the market that hadn't been served as well because of, one, the difficulty, but two, the amount of investment that had got into these critical larger mains that already exist.
Interesting. What kinds of things are like human-sized pipes used for?
I mean, sewage systems, when you get down towards these processing facilities, will get quite large. I know Tokyo has flood management systems. So a lot of stormwater will get quite large as well. You might have seen them. But I know Tokyo has one of the biggest underground man-made cavities just for processing and filling up all their monsoon season rain. So to process that amount of water in an urban area, you do need humongous pipes in some applications.
What do they do with all that water?
Question. I mean, if it's stormwater, often it just goes out to sea or into a local river. And if it's sewage, then it'll get processed before being released out, at least in, places where they're keeping to, good standards.
Well, one of the questions I quickly had sort of on that was like, what happens to like all the dirty kind of sewage water that goes to like a processing plant?
Yeah. So, I mean, there's different things that they can do with it. Some waste facilities these days are trying to make like biofuel with it. There's a whole process that goes into like separating out the water with the more solid waste, and there's multiple stages of which it goes through before it's considered clean enough to re-enter the environment. There's a lot of methane that they extract from it. The way that these are processed varies from area to area, but I think the best way to go about it is to use that as renewable energy source, in my opinion, because it has applications to supplement the more fossil fuel based energy systems that we currently have. So that's an exciting part of the industry that I'm hoping takes hold more around the world.
Yeah, it takes me back to elementary school where we had to visit the sewage plants and learn all about it. But yeah, I'm curious. So you did a lot of kind of course, like market validation, figuring out these different systems, the technical validation as well. What was the point when you guys said, okay, there's something here, we can probably build a company and we're going to go out and like try it? What was that moment?
Yeah, so that moment was really centered around the first engineering prototype that was able to move in this form factor in a pipe. And so once it was able to do that and we saw all of this potential in the market, it really shifted from, a side project into, okay, we can try and make a business out of this. So I was teaching at the University of Technology Sydney at the time. Shion was across at MasterCard. We were bootstrapping the business, so paying our first engineer out of pocket. And that was really the point in which we were going through the stages of talking to all these different stakeholders in the industry and learning the best approach for entry. And I think that accelerated when we got into StartMate. That commercial push, the mindset shift, and I think the ambition that it instills in you was exactly what we needed at that point in time to go out and start selling robots to the people that actually will need to use them.
And while you were at StartMate, you also started generating first revenue, right? Even if the product wasn't really live.
Yeah, I mean, once you knew the pain points that these customers were really interested in and dealing with on a day-to-day basis, and once we could see exactly how our robot was going to solve those issues, we went out and found early adopters, the people who could see where this technology is heading and wanted to inform decision making and be on board with that process. So yes, it gave us early revenue, which is great, but at the same time, these design partners, as we call them, opened up sites for us to go and test on, allocated resources for monthly design reviews and engineering updates so that we can get a really tight feedback loop on all the decision making and iteration that we're making on our end. And I think that's, at this stage of the business, 10 times more valuable than the money, which does show conviction, but it's really their input that moves the needle.
And you then, you finished StartMate and then you raised your kind of, I guess, seed round. Tell us a bit more about what your fundraising experience was like. You also got some pretty good international investors on board. So yeah, I'd love to learn more about that.
Yeah, so that was the first round of institutional capital Shion and I had ever raised. So there was a lot of learning in that process. StartMate does a great job of kind of taking you through the ins and outs of how to structure and raise a round. We had some customer deadlines immediately after StartMate, so demos with them, some design partners coming on board. And so we held our round back a little bit. And I think that, especially with all the kind of outreach and visibility you get in going through the StartMate Accelerator, helped us in some ways. It kind of created a backlog of people who are interested in speaking to us. And we had kind of a line in the sand of a day when we were going to start fielding those conversations. So instead of, stretching this fundraising process out over many weeks or months, it was almost like we had that date and we just had back-to-back meetings from that day forward. And it created a lot of heat around the round as people, became interested and things were able to move quite quickly, which we were quite lucky in. As you mentioned, we were able to get Peak XV, which is Sequoia's Southeast Asia and India fund, into the round, and they had reached out to us after seeing our StartMate pitch. So I think StartMate was incredible for the visibility and also the kind of learnings that they give you through that process.
Right. And yeah, that's probably like almost 6 months ago now that you closed that round. What's life been like ever since? You have an office now, which is quite cool. You have a team around you. What have the last 6 months been like?
We've grown this team size, which has been great. So the team's gone from 4.5 people to 10. And that's really to support all the different aspects of this engineering system that we're developing. We've engaged really closely with our customers, so spent time on site with them, going through, a lot of their software systems. We have a data platform where all of the data from our robot syncs, but there's so many optimizations and things that we found that our customers are dealing with that we can fix just on that side of things before even deploying robots into the field. So it's been great to really engage with them and understand the ins and outs of and nuances of their day-to-day work and continue to, get their input on building these ferrets and making them exactly what they need for their daily operations.
And what's your timeline? Yeah, go ahead.
I was gonna say, what's the big vision? You mentioned drones for like below ground. But like, with the drones, I mean, it's not really like, I can make a drone right now and just buying some off the shelf parts. And sort of the enabling thing with drones has just been, I guess, partially like, I don't know, just a lot of consumer electronics creating like a lot of kind of glut of like components that are cheap, that are easily available from China. And there's been a few like big companies like DJI that just get really good at building hardware, right? Like, and I guess, I don't know, like, and now there's also obviously military applications for it, and Ukraine's gotten into the game. But I think what you're building is slightly different in the sense that like you're creating, like you're kind of operating in a very constrained environment and in a very kind of high regulatory environment. But there's also a lot of missing data in some ways, right? So you'd sort of mentioned to us that you were thinking about at some point offering like a Google Maps of like the sewer system, right? Of pipes. So like, yeah, what does that vision kind of look like? Because I think it's actually like on the face of it, it doesn't. Maybe it seems like kind of an easy way to describe it, like drones, but for below ground. But actually, like fundamentally, I think it's quite a different kind of vision, right?
Yeah, there's definitely nuances that go into operating in a piped environment, especially one that acts as, critical infrastructure for whatever city or nation that it's a part of. The interesting part about the PureLink platform, I think, is the modularity. So when we say have the same impact as drones have had above ground, there are so many niche applications for piping infrastructure. I mean, it's used so commonly to transport all sorts of resources, and that presents so many different niche problems that people want solved. And so by creating a modular platform and enabling access, what we want to facilitate is an ecosystem of companies building on top of our robot. And so these companies already exist. The engineering companies, mining companies, sensing companies that have spent significant amounts of money on R&D for a particular tool or sensor or thing that they want to do, but then they have no way of actually getting that to where it needs to go. So the cool thing that I think drones have facilitated above ground is so many companies have been able to find an application for drones and then commercialize it. I mean, in Australia, Propeller Aero, and there's so many different companies that have been able to do that globally. And I'm hoping that the PureLink platform is able to create that same impact, but for below ground infrastructure in the way that we could never take all of these different niche applications and create a solution for them and create every modular add-on. But by opening it up, it becomes the base for all these different applications that we could never have even thought of.
Well, what is but what does the kind of company look like? Like imagine like 10, 15 years from now, what does PureLink look like? What do you guys do?
I think there's two very distinct sides of the business. There's the almost robotics as a service, robots that live in live pipes. And those are more larger contracts with people like utilities and, these big players in the industry. And then there's also the more mass market, affordable platform that is enabling people to build on top of. And so that doesn't have the same requirements and challenges in terms of living in pipes. And, that's a separate aspect of what we do. But in terms of creating this platform, increasing the reliability and economies of scale as we grow, we can kind of continue to bring down the barriers of entry and get this more widespread on that front.
Interesting. So you see sort of like you servicing contracts for like utilities, and then separately you having like a platform for other companies to sort of build on the hardware platform for their own niche applications. Is that kind of the right way to think about it? So I mean, so you're both kind of like a service company and a platform. Like, why not just do the platform part? That seems easier, and like have other people use your platform to do the service piece themselves.
Yeah, and I think that's definitely where we've started and what's kind of the next step for the robot. But I think it's much harder to achieve the same level of impact with just the platform play. To get fleets of robots that talk to each other, that are constantly living in pipes. Yes, that's not easy. That's definitely the moonshot goal. But it also has the most potential in terms of impact. Globally, 30% of all our fresh drinking water is lost to pipe leaks. That's, 4%.
How much? 30%.
That's the global stat. In places like Europe where they've got really old pipes, it's higher. Mexico City, where the city is sinking, so they have so many problems with their underground infrastructure. The shipping, they're bringing tankers full of water in because they can't maintain it. So there are definitely places that it's much worse than that 30% figure. Here in Sydney, I think it's about 12, 13%, which is better than that global average. But you've also got places that are constrained in terms of their water supply. I mean, a couple of years ago, South Africa almost ran out. Not South Africa, sorry. Cape Town in South Africa almost ran out of water. And that's just going to.
How do you run out of water?
Yeah, they came really close to what they called day zero. Their reservoir, their dam, was being used at a faster rate than it was being replenished. And what that means is, as climate change continues to worsen in certain regions and water insecurity grows, there will be more and more cities that go through dry periods and use their entire water supply before it gets replenished. That was kind of almost the case when PureLink was conceived. We were under water restrictions. Warragamba Dam was getting low. And so it's something that I think might be uniquely Australian in the sense of we've grown up around it. We've had water restrictions. It's the land of droughts and flooding rains. And so we see that juxtaposition of we can run out of water. It's a thing that can happen.
Doesn't happen in New Zealand, I guess. But I guess the bigger vision of like having these kind of autonomous robots or a fleet of robots going through the pipes, what are the biggest kind of engineering challenges to get to that place?
Yeah. So there's three key challenges that you need to solve. The first one is a form factor that can navigate and withstand that environment. So you're looking at about 120 psi is the standard, water pressure that you would experience in a water main. Sounds like a lot, but it's about the same as about an 80-meter water depth. And there's hobbyist, submarines that go down to that level. So that's okay to deal with. The next part about it is autonomy. It's got to be able to make decisions inside of the pipe with no human operator or human in the loop control. So that requires, significant amount.
Why is that? Why is that important?
Well, if you want economies of scale of fleets of robots out in these pipes, finding and fixing leaks before they become a problem, you would either need to scale a team of humans to control each and every one of these pipes, which is quite difficult to do, or you facilitate that through autonomy. And I think that's where robotics is heading in terms of the efficiencies that it can introduce. That's something that I think we have a unique advantage in as we start to roll out our robots into more pipes. We collect more data and our robots get better and better over time at making decisions inside of these environments. And then the third aspect of that is your power and communication. So your power system, as I mentioned earlier, there's so much kinetic energy running through a pipe. That's a relatively, I say simple, but it's a relatively obvious one to tap into. And then communication. You really have to use low bandwidth flags with really long wavelengths that can penetrate through the ground. So you have to, be able to indicate really simple things like leak here, blockage here, because you're not going to be able to stream out HD footage or provide a point cloud of what's going on. So it is really reliant on that autonomy to be able to make those decisions.
And do you think the robots could actually repair the pipes themselves?
Yeah, that's what we're pushing for.
No, I was going to just ask how does that work?
It depends on the type of pipe. There's all sorts of different, there's pipe relining that already happens. And so you can do things like UV patch, ceramic patch sealing in certain types of pipes. So that would need like a little applicator that would press this patch against the pipe and then just UV light to cure it in place. You've got spot welding. So if it's a metal pipe, you can put a little, TIG welder that just sits inside and just will seal a little crack in the pipe. Obviously, it depends on the magnitude of the problem. If a pipe's collapsed or something like that, it would be a lot more, hands-on to deal with, and you would need service teams out there. But for proactive maintenance and making sure that things don't get that bad to that extreme level, you can look at little solutions that allow you to remediate issues before they grow.
Interesting. I mean, how far away is that, do you think? like on your timeline? Like when can you have the first like pipe fixing robot out there, like fixing pipes?
We don't know if we're going to be the ones to make those modules in-house or whether it will be a partner yet. Maybe we have a specific application that we focus on and other partners build these modular add-ons for their specific ones. There are existing in much larger pipes, robots that can do spot welding and things like that. So these companies may see the PureLink platform as the logical next step for their existing technology. And so that's one of the exciting things about being a platform is we don't know when people will add these kinds of things on or what the kind of first one will be. But we know as we progress and we perfect each aspect of the robot, we will try and add as much as we can.
Like 5 years or 10 years, like if you had
definitely
to guess.
in the next 5 years.
Curious.
We will be attempting to do it ourselves in the next 5 years for sure.
And how would that work? Like, would people just buy robots and then manufacture the add-ons themselves and just like, and would pay you for what's like, is there some kind of like other, like some analogy of other companies doing something similar? Like I get the idea. It's kind of like a hardware kind of app store in some ways, but like, are there any hardware analogies of companies kind of like doing that?
Yeah. I mean, we kind of think of it almost like the Apple ecosystem as well, where third-party add-ons do need to be approved by us. Obviously, there's safety concerns and all sorts of stuff that goes into it. The analogy is really like a lot of modular ecosystems and add-ons for gaming often need to be approved and integrate with, Xbox or Sony or things like that. In the same way that exists in those industries, it can exist in heavy industries like pipe.
Oh, interesting. And so for Sony and gaming, is that like what like people build their own like controllers or something?
Yeah.
And then just sell them as?
Yeah, for sure. Controllers, there's all sorts of, like headphones that you can get for your like these are all add-ons that communicate through existing standards with pieces of technology we already have. And I think that's what brings the value up of ecosystems. So the same way the App Store, if you were to make a one-on-one copy of the iPhone that didn't have the App Store, it's not a real competitor because the value is really in the ecosystem itself. And that also goes for first-party modules. So the things that we make in the same way that, your AirPods work really well with your MacBook and your iPhone, we will make first-party modules that solve challenges and critical challenges extremely well.
Interesting. How do you charge those robots? If they're supposed to be like kind of circulating through pipes continuously, right? Like they're like your average suburban neighborhood circulating through pipes, and yeah, how do you get them charged?
So during peak times, so when people are getting up in the morning and also coming home at night, our technology, the drive technology is non-back drivable. So if you are to power off the robot or stop it in place, it's not going to move. It's going to stay locked into that position. And so what that means is a little hydroelectric generator that's on board can just allow all that water that's flowing past it to create energy. And then by the time that peak period is over, the robot can continue inspecting until, the next morning or the evening when the next peak period is. So that should allow you to leave these robots in pipes for extended periods of time. And I'm really excited about the applications that has in making sure this critical part of our societies, our cities is maintained in a way and treated in a way that it really should be.
And do you have that generator on the?
Yeah, I mean, all you need is a little turbine and essentially a generator, which is the same as a motor. It's just you spin the turbine with the water going past and that will recharge the batteries. And, that's, I mean, I say simple as that. Obviously, there's nuances that go into any system, but it's a feasible piece of tech.
But I mean, like, do you already have a space on the current kind of like, version of that, the way you put it, or where would you put it?
Yeah. So as I mentioned earlier, the modularity, each of these black lines is essentially a modularity point. And so although we've got this in the 2-drive form factor at the moment, you're not constrained in terms of length in a pipe. So what you do is you just add another linker on, which is that flexible mechanism like this. And then you add whatever module you want here, whether it's recharge, whether it's repair, whatever the case may be, and then another drive module. So you can just keep chaining these back on to create and
Mm.
add more functionality.
But does that
Very cool.
does it block? Well, I guess two questions. I mean, if you're chaining, it feels like the fan or the whatever rotor that you're using to recharge, isn't it fundamentally like blocked by the drive module? How do you actually make sure it's bigger? How do you make sure the water actually passes through it versus it just kind of goes around it?
Yeah, so the goal is for the cross-sectional area of the robot to take up 30% or less of that kind of volume of the pipe. And that's to ensure that there isn't a significant pressure drop on the other side of the robot. These systems can continue to work as intended. How we kind of approach that from a turbine perspective, you can get blades that can kind of extend out, so they would be wider than the existing profile of the robot. We've got a few ideas on how we would approach that. It's not something that we're actively adding on to the robots at the moment as we tackle this first path of commercialization in sewage and wastewater. Turbines are relatively solved in existing technology, so it would be just about what is the most effective and also reliable way to add this to the robot.
I feel like Mark wants to come and work at your shop for a little bit.
More than welcome. More than welcome.
I want to ask you just a broader question on robotics. So PureLink is obviously quite a narrow kind of use case, focusing on pipes. We chatted a little bit about humanoids earlier. What do you think the future looks like? Do you think we're going to see a lot of kind of, single use case, like narrow use cases in different robotics? Or do you think there's a future where we have humanoids kind of, the Tesla, I guess, vision of like having every human has a humanoid kind of running around doing the laundry and that type of stuff? Like, yeah, how do you think that future looks like and how far away is that?
Yeah, I think we've done a pretty incredible job at engineering the world around us to suit our needs and our form factor. So I think the humanoid robotics market is enormous and the applications are incredible. How soon that really becomes, a big part of our everyday lives, I think is sooner than everyone thinks. I do believe it'll start with that more teleoperated model, as they use that almost as a way to train these robots in the same way that Tesla has had autopilot or self-driving for the last 10 years. But the key kind of part of that is collecting all the data and seeing what drivers are doing with all their cars can go back into this robo-taxi next kind of stage that they're trying to pursue. I do think there are definitely applications as well where humans are not the best form factor to go into. Pipes is absolutely one of them, but there's places like
one of them, yeah.
Power lines. I know there's different form factors there. There's companies working on incredible different, form factors that are suited for that environment where a human might not necessarily be. But I think in our cities and our everyday lives, the most visible robots will definitely be humanoids.
I mean, what's interesting because it's taken Tesla Waymo sort of got there faster in some ways. I mean, I don't know. It's they've taken two different approaches, right? Where Waymo's like, hey, we're going to train like in just certain cities and like roll this out in certain cities and just basically just get really, really good at like that specific geography, versus Tesla was like, we're going to get data from all over the world and then eventually kind of like start releasing it slowly and still kind of supervised. And I feel like we're sort of, on the cusp of like, sort of self-driving really becoming a thing. Like I think, it's now a thing, and like at SF, San Francisco it's like it's a normal thing now. I think there's parts of the world that like they still think it's like the future and like very far away. But a big part of it is like, I think also not the engineering part. It's also like the regulation, right? And just like, is this thing going to kill a person? And even though it's like safer on net than a human driver, there's still like a higher bar for it to clear. Which, like, I don't know if that makes a lot of sense, but that's just it is what it is. So like with humanoids, like, do you think we'll have the same kind of issues and problems where like, like in some ways maybe you'll get to, like right now it's like it can't solve tasks autonomously for the most part, so you need someone to supervise. But at some point it will be, and then will the regulators still say, well, actually it still needs to be supervised just in case?
I think it'll definitely depend on what task it's undertaking. I feel like for low risk or low priority tasks like doing your washing or whatever the case may be, that will be relatively easy and it should be unimpeded by the regulatory side of things, at least in my opinion. As it gets out into more complex use cases, like maybe go down to the shops and pick up my groceries and come back, and it's interacting with the wider world, I could see a world where there's robot-free zones, or there's a ban on certain types of robots because they keep jumping out in front of traffic or doing something, that does create an unsafe environment for everyone around them. So I could absolutely see things being implemented in that sense. But I think in the home is kind of that first relatively easy testing ground for these companies to start, using their robots.
But on the other hand, I guess if you think that supervised learning is kind of the way to train these humanoid robots, maybe the home isn't actually the best place, right? Because there's being from Germany, there's privacy concerns. Like that's our number one topic. So maybe the best place for these supervised learning humanoids is like a restaurant or something like that, right? Where you just kind of do the dishes or whatever.
It's a big topic in Germany because everyone walks around naked. That's what I hear from Henrik.
In my house, yeah, for sure.
Fair enough.
So people don't want robots in there.
I know Figure AI is putting their humanoids in like factories. I think they have a big deal with I believe it was BMW. There are definitely places where I think it's probably easier for them to control the environment and safer. But yeah.
Yeah, I think it's gonna be a super exciting future. And I think we're super excited to see the ferret robots going into the pipes. They're going to be, so I guess the testing ground is going to be mostly Australian cities, Sydney.
Yeah, initially. We definitely want to get across to the UK and the US as soon as we can. The UK is a big market for us, just really old pipes. All the water utilities are privatized. So there's a lot of work to be done over there. And the US, as always, is a massive market. So we try and think on a global scale from day one, but the initial deployments over the next few months will be still here in Australia. Yeah, stay tuned.
Hey, Harrison, did you ever consider calling the company Piper?
I thought about Pied Piper with a direct kind of nod to Silicon Valley, but I think that was a bit too on the nose.
Yeah, I think Mark wants to sell his domain.
That's
so
right.
Just give him a call.
If you want to redirect it, I'm more than happy to take the extra traffic.
Cool. Well, this, it's been super great. Such an exciting company that you're building, and we're super excited to be on board. Yeah, we'll drop by the office sometime and see how you're going.
Sounds good. Thanks again for having me. It's been great to chat.
Awesome. Congrats,
Thank you.
Thank you.
See you guys.
Thank you for tuning in to TechMates. If you enjoyed this episode, be sure to subscribe, leave a review, and share it with friends. We'll be back soon with more stories of Kiwi and Aussie founders reshaping the future and disrupting down under. Until next time, keep dreaming big and daring to disrupt.